everyone. Tonight we have a special treat provided by the organizers of Strings 2016, which is being held here in Tsinghua University. Two public lectures by two of the most accomplished theoretical physicists of our time, who are also two of the most accomplished public speakers of our time, Robbert Dijkgraaf and Nima Arkani Hamid. The first speaker, Robbert Dijkgraaf, I was just remembering meeting him for the first time almost exactly 30 years ago on the island of Capri. He was still a young graduate student, but already clearly brilliant, and shortly after we managed to bring him to Princeton. He's had a fantastic career as a string theorist and a mathematical physicist. For many years, Robbert led string theory in Holland, in the Netherlands, and played a very important role, not just in string theory, but in Dutch science, where he became the president of the Royal Dutch Academy of Sciences. And then in recent years, he was attracted back to Princeton, where he is now the director of the Institute for Advanced Study at Princeton. Robbert has many qualities, but perhaps the most unique is his artistic, the most unique for a physicist is his artistic abilities. Robbert actually contemplated being an artist before the beauty of physics captured him, but he's still a fantastic artist, and often I have one of his pictures, which was done for strings at one of the string conferences at Santa Barbara in the 20th century. And you will, I have no doubt, see some of his artistic qualities in his lecture tonight, which probes and is entitled "The Frontier of Fundamental Physics." Robbert.
Thank you, David, for this very kind introduction. And I'm happy you didn't introduce me as the best painter among physicists or the best physicist among painters. I think both of it is a dubious honor. It's great to be here with this wonderful string theory meeting. In particular, I think, for those of us who were here 10 years ago and just admire the progress being made in China at all levels, and so see so many particular young, brilliant students, many of them here in the room. I will have kind of want to talk a little bit about the long arts of theoretical physics, and this cartoon that appeared in a Dutch newspaper a few years ago captured it well. Nature's working, but does it also work in theory? And that's what we figure out. And I want to begin with a few slides indicating the kind of long arc of theoretical ideas. So of course we all knew this great news of the discovery of the Higgs particle. And I was very happy that I could attend the ceremony where Peter Higgs was giving the Nobel Prize. But then I was sort of noticing that on the backside there are all these former Nobel laureates. And of course here's David Gross. And my thesis advisor was there, and then I was wondering how come that these younger physicists already earned a prize while Peter Higgs hadn't, and then you just realize that he was kind of unlucky of making a 50-year prediction. In fact, there's this kind of wonderful list that appeared of all the particles of the Standard Model, and the time from their theoretical assumption to their discovery, and the Higgs kind of set the record. In fact, there's also here the muon, which famously was first discovered and then predicted. A second example, of course, that you all witnessed was the detection of gravitational waves by the LIGO laboratory. This wonderful occurrence of a merger of two black holes. And in that case, in fact, we go back all the way to the year 1915, when Einstein wrote down for the first time his equation. So we could add, in some sense, the graviton to the list and see of this as a 100-year prediction coming now. So I think the summary of that is that we're living in an incredible, exciting time when we have these kind of long-term predictions coming to fruition and really changing the landscape of physics. Now, I also want to say something about the kind of use of these discoveries before I start my the rest of the talk. And there's this wonderful essay written by Abram Flexner, the first director of the Institute for Advanced Study, about the usefulness of users' knowledge. And there are kind of many, that's a wonderful term that captures a lot of what theoretical physics does. There's this famous saying of Faraday when he was asked, you know, what's the use of electricity by the British Chancellor of the Exchequer, one day, sir, you may tax it. And of course, there are many other examples in quantum mechanics, you know, which was just such a struggle to, for the first pioneers. And now it's estimated that 30% of the economy in the US, for instance, is based on quantum mechanics, if it's not more. My favorite example of this actually is the theory and the phenomena of superconductivity. It was discovered more than a century ago. A wonderful phenomenon that, of course, allowed the building of very large magnets. And so, in turn, it not only led to all kind of technology, but led to the discovery of fMRI scanners, and basically it started the whole world of neuroscience. And in fact, it's also now a critical component in quantum computers. But the largest magnets can be found at the LHC. So in a very indirect way, a discovery of a fundamental phenomena in physics led to the Higgs particle and actually probing the frontiers of high-energy particle physics. And of course, in a wonderful circle, that theory of the Higgs particle is again based on the theory of superconductivity, showing how everything is connected. Now, in principle, it's not obvious that theories of high-energy physics, which look like this big mass, have beautiful theoretical descriptions. And so for quite some time, there was a thought that perhaps nature is a black box, that you cannot really open it, and that you just can measure and there's nothing there to probe. Well, it turned out to be completely wrong. The black box could be opened. And of course, we all know there's this wonderful theory of the Standard Model describing the elementary particles. Now, using fancy mathematics, you can basically put this whole equation on one line. And it's remarkable that all the ingredients in that equation are perfectly natural mathematical objects. Now, this is another way to write the equation with in all the symbols. It's actually in Veldman's book. I would always like to say, well, you can also put it on a t-shirt. In fact, now with the Higgs particle, so 70 particles capturing everything around us, that's a tremendous success. Tremendous success. If you look at for instance, the particle data book, that these few particles allow us to compute all composite particles in great detail. That's an amazing success. And of course, it's based on fundamental ideas, particularly the idea that we have elementary processes, some of possible diagrams that we can compute with incredible accuracy, some of them into 12 decimal points. And if you ask what is the true fundamental principle underlying particle physics, it's actually symmetry. And a simple way to visualize this, if you think, for instance, of the theory of quarks, very happy to give this example in front of David. Quarks come in 3 colors, so you can think of this as a little vector that's rotating in some kind of internal space. And in fact, you can have these vectors on every point in space-time. And in fact, you can rotate them individually, independently, at each point of space and time. And in an intuitive way, you can think of the waves of these arrows as describing the gauge fields that propagate the fundamental forces. Now, in the world of quantum mechanics, that have to be given by these Feynman diagrams, and we get kind of the gluons, which are particles that can interchange colors, and they will, in a natural way, produce a matrix because any color can change to any other color. So for quarks, it would be 3 by 3 matrix. Now, Nima will say much more about I hope, about the puzzles of the standard model. And there are like two reactions to it. One of it is a great beauty and elegance. The other one is, well, who ordered this? You know, why these particular particles? And theoretical physicists start moving them around and seeing whether there are other patterns to discover. And for instance, you know, with the assumption of a massive neutrino, you can try to put these particles in a more beautiful and richer symmetry structure. For instance, an SO10 symmetry group. There are attempts of unifying these forces, and there are several indications why we should be able and should want to do this. The most important thing is that the fundamental forces in nature, when you probe them at higher and higher energy, their strength becomes more and more comparable. It looks like the forces want to unify, and you can make that more specific by looking at the strength of these interactions and probe them at higher and higher energies, and you see they're getting very close to unifying. In fact, you can make this much more precise by including yet another symmetry, supersymmetry. Supersymmetry is, again, a very tempting idea that's part of our theoretical toolbox. In some sense, you can say it kind of explains what I would like to say almost a central dogma of particle physics, namely that nature is made out of particles and forces, radiation. And supersymmetry will relate these two categories. The bosonic particles that describe the forces, and the fermionic particles that describe the magnetic fields. Now, again, you can think of this as an extension of our ideas, because supersymmetry will mean that instead of just the ordinary commuting coordinates of space and time, we would add anti-commuting coordinates. So discovery of supersymmetry would indicate essentially an extra dimension, kind of an infinitesimal dimension, pointing in an anti-commuting direction. Now, there are other indications that we are looking for more to complement the story of the standard model. The most impressive is perhaps the presence of dark matter. We know that there are huge clouds of unknown matter surrounding our galaxies. We know that this dark matter is actually absolutely crucial in the formation of the early universe and the distribution of galaxies and stars. We know through measurements of cosmology in very great detail exactly what the energy content of the universe is. And that's perhaps the most surprising element, that these measurements tell us that roughly 95% of the universe is still missing. That is to say, it's made out of new forms of matter or new forms of energy that we totally do not understand. So from a theoretical perspective, there's a great urge to extend our ideas beyond the 5%, which is so beautifully captured by the standard model. And again, this is also the 95% that we want to explain is deeply connected to our understanding of space and time. So in quantum field theory, you can have so-called virtual particles. These are particles that can exist for a short time. For instance, a particle can split into two and then recombine again in a brief time. And in fact, you can have even particles appearing out of nowhere and then disappearing again. These are so-called vacuum diagrams, vacuum fluctuations. You can think of these as almost particles that go around up and down into time. Now, according to our insights, space-time should be filled with the gas of these virtual particles. They're continuously appearing and disappearing. And the way they imprint their presence on reality is that they kind of add to the energy of space-time. So we think that dark energy is a reflection of these vacuum processes, which are totally not understood. And it turns out so that through the mechanism of quantum field theory, empty space is filled with these phenomena that we truly want to understand. Now, often I think that, in fundamental physics, we are a little bit like the old map makers who had charted a part of the world, but the large part was unknown. And they didn't really dare to leave the map open, so what they did, they put all these kind of sea monsters there. And of course, there are no sea monsters anymore. But I would like to say that in some sense the things that I'm talking about now might be the sea monsters for future experimental results. We are kind of imagining what's out there beyond the shores of the world that we have mapped. Now, crucial to this is bringing together the two fundamental theories that we have in theoretical physics, the description of the very small through quantum field theory and the very large in general relativity. And so we'll be talking about quantum gravity, which is the attempt to bring these two worlds together. And we know we have to do this because there is only one world, the world that we're living in, that clearly has both components in it. Now, just in a few words, gravity is completely orthogonal in terms of its descriptions to the way we understand particles. As Einstein told us, gravity is the manifestation of the curvature of space and time. If you put something in space-time, it will start to kind of curve, change its shape under the influence of the distribution of energy in matter. And it's the motions through these curved spaces that we recognize as the gravitational force. Which is a completely different description than in the terms of the Feynman diagrams that we describe particles. So, in particular, since gravity is described by the curvature of space-time, we can have little waves in space-time. These are the gravitational waves that we now have experimentally discovered. And if you take the next step, you think of these gravitational waves at the quantum level, there should be a particle associated to it, a graviton, the spin 2 particle. And you might think about, and that's, as a particle physicist, what would happen if you start to scatter these gravitons together? And you find actually that this gravitational strength is given by Newton's constant, which is given by, you can think of units of a mass, the Planck mass. I will come back to that. And the fact that it's dimension-full quantity means that it's so-called non-renormalizable theory. So loop diagrams, quantum effects in this theory are problematic. To explain this Planck length, it's good to do another exercise to compare the gravitational force to the other forces in nature, for instance, to the electric force. And one way to visualize this is to think about how heavy should a fundamental particle like a proton be in order that the gravitational force is comparable to the electric force. And it turns out that roughly the proton should be as heavy as a bacterium, which is incredibly heavy on the scale of high energy physics. In fact, it means it's 10 to the 19 times more heavy than an ordinary proton. So the gravitational force is incredibly weak. And that means that if we want to look at the quantum effect in gravity, we have to go to incredibly small distances which compare to very large energies. So the Planck length is the fundamental length that we think describes the distances where gravity, the gravitational fields, become a quantum mechanical object. So we have kind of this floating or curving space-time. So one way to think about it is that space-time is a little bit like this picture, nice picture of Planck, that if you zoom in and further zoom in, you get kind of pixels. And these pixels are in some sense of the Planck length. That's the way you might can think of it. And so, in some sense, it certainly gets the very big picture. So the remarkable thing is, if you think of the length scales in physics, we have an absolute smallest length scale. We have an absolute largest length scale, which is the length scale of the visible universe. And to orient yourself, we, or human life, life itself is roughly in the middle of that. And you can think of basically human beings moved as far as like 1/4 on this logarithmic scale to the right. And this is the scale where our particle physics experiments are. So in some sense, we map 3/4 of that range of dimensions. And the thing still left is this kind of first quarter, going to smaller and smaller distances. By the way, one of the most exciting ideas around, I won't have any time to say something about this, is the idea of cosmic inflation. Cosmic inflation would be beautiful because it would in some sense connect the physics at the very smallest distance scale to that of the very largest distance scale. And so there's also a very beautiful way in which these two ends are meeting, and actually both in our experimental observations and in our theoretical ideas. So this is a string theory conference, and of course I should tell you something about what string theory has to do with this. So again, let's go back to particle physics. And the scattering of gravitons. Now, we have seen interactions of particles with this property that they are non-normalizable in the past. For instance, the theory of beta decay in radioactive decay. There was originally the Fermi interaction, the Fermi theory, where particles are scattered with a strength that was also proportional to 1 over mass squared. And this theory now is part of the standard model, and we resolve that kind of singularity by saying, well, there's actually a fundamental particle that's doing this exchange, is the W boson. And in fact, that W boson has a certain mass, and that actually explains why this interaction has this particular property. So kind of following that idea, you might think that in quantum gravity, similarly, there's an intermediate particle or object that would actually carry the interaction and would be roughly have the weight of that particular mass or energy scale. So in a very naive way, you can think of what this is the way string theory starts to kind of regularize gravitation. It's introduced this kind of intermediate object, the string. In fact, the theory and the history of string theory goes back to the 1960s. And in some ways, string theory is part of our standard description of understanding particles and fields. For instance, if you somehow in electromagnetism go back from Maxwell to Faraday and think of electromagnetism not in terms of gauge fields, but in terms of flux lines, and then start to think in terms of flux lines about quantum thermodynamics, you in a natural way get to kind of string theory, because there the flux lines will be kind of glued together. That's the phenomena of confinement. And so we think that in QCD, in the theory of quarks and gluons, there are string-like objects. In fact, there can be two kinds of strings. There can be open strings that connect quarks. These would be kind of the mesons. And you can have kind of closed strings, which will be little tubes of these glue balls. So strings themselves already manifest themselves in our standard theories of elementary particle physics. But of course, we want to apply them to the theory of gravity. And so string theory has this wonderful property that since it's an extended object, it can vibrate, it can have kind of harmonic oscillations just as ordinary strings that manifest themselves in terms of a whole spectrum of particles, where the particle on the bottom, the massless particle, would actually describe the graviton. So from a mathematical point of view, what a string theory is, it's a little loop and it will propagate in space-time and will sweep out, instead of Feynman diagrams, it will sweep out these world sheets, two-dimensional surfaces. And one of the most powerful properties of string theory is that these interactions are entirely geometric. You can see by just kind of drawing diagrams, these surfaces with more complicated topology, that the interaction vertex is given by the geometry of the string. There's no need to specify which particle interacts with which particle. It's totally done in a natural way. And in the same way, loop diagrams are captured in a completely elegant and natural way by introducing diagrams of more complicated topology. So if you think about string theory, you can think of it as a generalization of particle physics in two possible ways. So first of all, there's something which we call the string length, which is controlling the size of the string. And the second parameter is the string coupling. It's somehow you can think of it as Planck's constant. It's controlling the way the strings can interact. And so you can kind of think of a little bit like a phase diagram of string theory in terms of these two variables. If both of them are small, we are thinking about particles. If you tune up the string length, instead of particles we have little loops. If we go in the other direction, so introduce basically the Planck's constant, we go to quantum fields for particles. And in the case of string theory, we get strong coupled string theory, which I will in a moment say has very close connection to the theory with branes. So you should somehow think of string theory as a generalization of space-times in a kind of a two-step process. In some sense, there is a first step where you think of it as a stringy geometry, so you look at space-times through the eyes of little loops. And then there is a more quantum version, if you go even smaller distances, where really the full quantum geometry should manifest itself. Now, an important element of string theory is that the role that geometry plays is not only the geometry of our four-dimensional space-time, but internal dimensions play a crucial role in the description of the theory. Now, this idea is very old. Already in the 1920s, people studied extra dimensions. There's the famous Kaluza-Klein theory, where you add a fifth dimension, the circle, and if you study general relativity in this five-dimensional theory, you naturally way obtain a theory of gravity and electromagnetism in four dimensions. Now, string theory is a massive generalization of this idea, where we have not one, but 6 or sometimes even 7 internal dimensions that can be curved and compactified in a very complicated way. So there's a study of these, for instance, Calabi-Yau manifolds and other internal compactifications that are part of the way string theory is capturing the physics of particles. In fact, there's something we call geometrical engineering. You can, in some sense, make a dictionary where the particles and forces that we see in 4 dimensions are directly related to the way the internal dimensions are curved and are compactified. That's by itself beautiful, but it also, we have a very kind of an extra insight that is perhaps even more powerful. Because if you think an ordinary geometrical object, it's very difficult. Well, there comes in various different shapes and sizes. And to go from one to another is usually a very singular process. You have to kind of tear the space apart. You have to go through the singularity. In string theory, in some sense, the spaces are fuzzy, and it just happens that you can have smooth transitions from one space to another. In fact, this is a very powerful principle, perhaps the most fundamental idea that came out of string theory. And that all these possible compactifications, that in terms of classical structures would be disconnected components, they're all part of a big space of possible theories. So string theory comes with this enormous, gigantic moduli space, which has various kind of classical limits. So there are various classical limits you can take, and just give you an example of 2, where 2 spaces x and y appear in some sense in a limiting process out of full quantum string theories. And so part of string theory is not only studying a particular background, but studying the whole space of background, this large cosmic landscape of possible compactifications. And this could have crucial results for cosmology. I can't say much about it, but if in theories of inflation, the universe could be much larger, could have various branches, various pieces, where parts of that landscape are being explored. So this again is an enormous extension of our usual ideas, both about cosmology and about what fundamental forces are. Now, the second important ingredient I want to mention that's crucial in our understanding of string theory is black holes. Now, black holes are a crucial part of modern astrophysics. We see them indirectly in many possible ways. But they also are crucial in our theoretical understanding. I think it was first John Wheeler who said how surprising it is that the laws of physics also encode the end of physics, of the breakdown of physical laws. We know that in the universes there are singularities. There are a particular singularity at the Big Bang, which was the beginning of time, and black holes are, in some sense, you can think of them as the end of time. And so they are as crucial to understand as the cosmological singularity. Now, one way to understand why a black hole is the end of time is this is the usual kind of diagram in which you see in space-time diagram, you see a star imploding and the so-called event horizon forming around the singularity. But actually, if you draw the arrows of time in this diagram, you see that actually inside the horizon, the time is pointing horizontally, and so it stops at the horizon. So you should think of at the singularity. So you should think of this black hole singularity really as a point where time stops, and that's why it's such a fundamental puzzle for physics. In fact, introducing quantum mechanics to black holes makes it even much more puzzling and richer. There's the famous phenomena of Hawking radiation. So if you look at these quantum processes that are described that are everywhere in space-time, in the neighborhood of a black hole, then you can have a process where some of the particles disappear inside the black hole and some particles appear outside the black hole. And this is our cartoon version of understanding the phenomena of evaporating black holes. So we think that in quantum mechanics, black holes not only form, but they will also kind of evaporate. And they, in some sense, look very similar to radioactive particles that are decaying. So they should be really part of our repertoire of the way we think about particle physics. In fact, the famous result says that the strength of this radiation is captured by the surface gravity, so there's a temperature we associate to a black hole. And more than that, we can also associate an entropy to the black hole. So one way to think about black holes is that they, on the one hand, are extremely simple. They're just literally a hole in space-time with an event horizon surrounding them. But under the laws of quantum mechanics, they become one of the complex variables, because you can also think of black holes as the most efficient way to store information. There's the famous formula, the Bekenstein-Hawking formula, that tells us that the geometric entropy, the amount of information you can store inside the black hole, should be proportional to the surface area of the horizon, measured in Planckian units. So we think of somehow as the degrees of freedom of the black hole residing on this event horizon. Now, remarkably, string theory gives an incredibly powerful insight in the quantum mechanics of black holes. And it does so by introducing yet another object. String theory is not only a theory of strings, it also has various other extended objects in it. In particular, it has branes. Branes are things which can have any dimension, and they have the property that the strings end on the brane. So you get diagrams like this, and these so kind of open strings, so little tubes tethered to this membrane surface, apart from the closed strings that we have, which are little loops. Now, the remarkable thing that if you start to study this theory of open strings, you can have not one brane, but many branes. So you can have open strings that go from one to the other. And if you kind of move these branes a little bit apart, you see that these strings now become labeled by two labels, I and J. So you get a natural way, an n-by-n matrix of these open strings. And in fact, the ways these open strings interact is just matrix multiplication. That is to say, the theories living on these branes, the open strings, are ordinary gate theories. So part of string theory is also gate theories living on these branes. And that gives a very different way to think about black holes. Again, this is a cartoon version. So here's the horizon of the black hole. Here are the closed strings. The closed strings should be able to describe gravity, so they describe the curvature of space-time. But you also can have open strings. So here we think of them as basically falling inside the black hole. And they are kind of described degrees of freedom close to the horizon. And so the process of Hawking radiation, you can, again in a cartoon version, see as a process where two of these open strings collide, form a closed string that will kind of evaporate, can kind of escape from the horizon. Now, all of this can be made much more precise by using the full mathematical force of string theory. And so a much more precise setting is the following, that you think of these branes actually as being inside the internal space. So this red thing is somehow the internal Calabi-Yau manifold. The green objects are the branes wrapping around it. And if you wrap more and more of these branes around it, the space-time, the four-dimensional space-time, will start to behave like a black hole, get the curvatures of a black hole geometry. So the geometry that is describes the black hole is in some sense emergent. It appeared outside, out of the study of these branes that are essentially described by gauge theories. So in the most powerful way, this was captured by Maldesena's work on the ADS-CFT correspondence. I won't go into the details here. But we have a rich dictionary describing how theories of gravity can be described by complementary theory, gauge theories, that you can think of as kind of living on the boundary of that space-time. So they live in one space dimension, one space-time dimension less. And so that means that string theory suggests a very different idea of quantum gravity than perhaps our naive fashion of thinking of little pixels in space and time. So we think that studying these theories, these UN gauge theories, where n is the number of quarks, which could be very large, have the property that if you take that number really infinitely large, which is the classical limit, you get nice space-time. If you do something where it's large but not infinite, you can compute corrections, you get kind of a little fuzzy space-time. And if you take these models at finite length, you get something which is kind of totally pixelated, and in some sense doesn't even resemble in any way a nice geometrical space. So I want to kind of end with a few kind of philosophical remarks about what this is telling us about the structure of theoretical ideas and space and time. So the seal of the Institute for Advanced Study has this beautiful two women, Truth and Beauty. I must say I have a t-shirt with them, and when my children were small, they were always embarrassed when I was wearing this t-shirt. Of course, one question is which of the two is naked? You probably have heard about the naked truth. And so one important question always when we have these theoretical ideas is about, what is more important? Should we follow the aesthetic of our mathematical equations, or should we be very careful and look what's out there in nature? Now, Herman Weyl has this wonderful quote that when he was asked how he made his choices, that he always tried to unite the true with the beautiful, but when I choose one or the other, I usually chose the beautiful. In fact, this is an even stronger quote by Paul Dirac. That's more important for our equations to be beautiful than to have them fit experiment. But of course, there's a complementary point of view. And I personally like very much this remark by John Wheeler. He said that every law of physics, pushed to the extreme, will be found to be statistical and approximate, not mathematically perfect and precise. And I think he has a very strong point. If you want your theory to survive, it better should be able to adapt and to be improved, and in some sense always have a margin of error. There's also a famous quote by Francis Crick from DNA discovery fame. Any theory that can account for all the facts is wrong, because some of the facts are always wrong. And so this is an important lesson for anybody who wants to have a unified theory of everything. But I think the ideas that are around in string theory kind of make use of both of these phenomena in a powerful way. In fact, you can think in some sense, it's kind of amazing that if you look where the most powerful mathematical ideas reside, where does theoretical physics become most simple, in some sense becomes at very high energy or very low energy. It's in cosmology and particle physics that we find the most elegant equations. And you can think like in the middle, you have large complexities, and you won't see them. So in some sense, we want to have kind of simplicity both in the very large and the very small. And there are kind of two mechanisms by which we can find simplicity: reductionism and emergence. So one part, of course, of particle physics is to think about reduction. Again, as I said, it's incredibly powerful. To look at the world around us, for a large extent, it's made out of matter and light. And we know that's beautifully captured by electro-quantum dynamics. And so, from a particle physics point of view, there's a lot of complexity outside, but that complexity can be reduced to a very simple number of building blocks, satisfying elegant equations, if we go to the very simplest level. Now, there's a complementary point of view, where simplicity actually emerges at the other end. So, for instance, if you want to describe a glass of water, it's not very helpful to do this in terms of 10 to the 24 water molecules. In fact, the laws of thermodynamics, the laws of hydrodynamics, emerge in the limit where you have an infinite number of particles. In fact, the laws of thermodynamics are a perfect example of a law of nature that satisfies Wheeler's criterion, because it's never true. Because it's only true in a mathematical sense if you have an infinite number of particles, which in real life situations will not happen. So I think the most remarkable thing of the present state of string theory, that we have both of these processes working. Clearly, in the way I started the first half of my talk describing elementary particles and how they generalize to strings, little loops, which then have beautiful interactions that we can study in great detail, that's the reductionist point of view. But if you start to study quantum gravity and black holes, we take kind of the opposite point of view. In fact, there you would say that the theory of space-time, including the fields living on space-time, is not the starting point, but it's the end point. It's something that emerges out of the theory of whatever the theory is, that captures the quantum information that builds up black holes and perhaps even our space-time, including all the particles and strings on that space-time. So I think we see these two kind of arrows working at the same time. And I think that's perhaps, it's a big puzzle how all of this hangs together. But it also gives us an incredible sense of richness of string theory, because it basically combines the two fundamental principles that have been so successful in theoretical physics. So one of the remarkable things, and again, there's a nice thing of such a public talk that I can sketch the very large picture. So there's an even bigger picture than that picture that I described in the first half of my talk. So I said, in some sense, this is already 60 orders of magnitude that we want to understand, and we already are 3/4 of the way. But string theory suggests that this is not the end. I said, on the one hand, it might not end by our universe. There's a much larger story probably in cosmology, including the multiverse, including a landscape of theories. And on the other hand, it doesn't end with the Planck scale, because there might be something underlying this that doesn't have space, doesn't have time, doesn't have particles or fields, but is somehow capturing and are the fundamental degrees of freedoms of our theory. So that's an incredibly rich picture that I think stimulates all of us to work on this theory. There's another phenomenon happening, and that's my last remark. If you see what goes into string theory, it's kind of dizzy. I would say everything but the kitchen sink. All our ideas in theoretical physics are being used. And they somehow all seem to hang together. So we're not so much unifying all the descriptions in the world, but we certainly are unifying theoretical physics as a discipline, which I think is incredibly powerful. So one of the questions we have is, how do we describe this theory? Do we describe it in terms of little areas, little maps, in the way you describe the world in terms of an atlas of maps? So sometimes you have to use the language of relativity, then you have to use the language of particle physics or cosmology. There are all these different languages, and there are kind of dictionaries that allow us to go from one to the other. But is there a single unifying principle? Is there like a globe the equivalent of a globe in which you can see the Earth as it is. Something which would be this quantum universe, where all the theoretical ideas come to play. Well, I think that's in some sense the biggest question that we are confronted. But it's incredibly powerful and exhilarating that we're living in a time where all these theoretical ideas are coming together. Many of those of you who are graduate students or perhaps undergraduate students, you have the great luxury that in your research you can basically wander around and work on all these topics and you actually see the interconnections between them. And at the same time, we're also very lucky that we're living in a time, as I started my talk, when a once in a century and a once in a half century event just happened. And so I think there are many interesting and exciting experimental opportunities also in the near future. And so I think the message, certainly my concluding message, certainly for the younger people here in the lecture hall, is that you live in the best of times as far as the frontiers of fundamental physics are concerned. Thank you very much.
So I think we have time for some questions. And let me request that the people who ask the questions are not the participants in the strings conference.
String theory has too many data being appointed because too many conjecture. Although it's very beautiful, it's very less likely it's to be right. I heard it from a string theory physician. What's your viewpoint about his saying? Thank you.
Well, I think in some sense what we are seeing through the development of string theory is that actually there are less data, because what we thought in the beginning were very many different choices that could be made. We kind of now know that this kind of all is hanging together, and it's kind of this huge space of possible solutions. But it's a space of solutions of a single theory. So an important element, of course, in studying in the applications of string theory to the real world, to particle physics, is finding out what picked this particular solution in which we are living. And I think the honest answer is that we don't have the good ideas around it. There are some of them, but it's intimately connected to understanding the cosmological solutions in string theory. It's intimately connected to understanding the fundamental degrees of freedom of the theory. But what we see is that we have like many pieces of the puzzle. They fit very nicely together, but we definitely haven't yet all the pieces of the puzzle. So in some sense, the theory is definitely rich enough to include anything that we know about nature. It's also a theory that, as I said in the beginning, is already part of our description of nature. So if you want to, there are particular string theories, those that describe the strings that are living in the theory of the strong interactions, that are part of reality. So in that sense, I think string theory will stay with us. It's certainly one way to look at nature, but it's also at this point the only theory we have that in a precise way is able to address issues in quantum gravity and cosmology.
Do you think it is possible to build a theory of everything from the very beginning to the end of the time of the universe? It is possible? Is it possible?
Well, I think, first of all, I think everybody who's working on this field is driven by the feeling that yes, this can be done. And I think the results that we have are all very positive, pointing in that direction, because it actually is able, we are able to combine in our theoretical ideas the main elements, both of the very large and the very small.
Yes.
And I think, you know, this, my first slide indicates that clearly nature is working. We see that, you know, in our investigations. Whenever we make progress, the theory seems to be more elegant, more simple, have less constituents.
Yes.
So I think we're all extremely optimistic that such a theory can be found. But I think we also all agree that we haven't yet probed the theory deep enough to give such a description. So we are, in some sense, still being very close to the original ideas, where in some sense we could do mathematical calculations, very precise. But it's, we are not yet at the stage where we have a complete description of that theory. But I think there's a strong sense that such a theory exists, and that's describing our world.
Yes, thank you. And I have some ideas about this. We have already built a theory like this. Seemingly, it will work. It will work. Thank you.
Hi, so I want to ask you what do you think of metaphysics? Because I mean, in physics, in a really small scale, you know, lots of people have they suppose some questions. For example, the universe is made of masses, tiny dots. For example, so what do you think of these ideas? Or I think it is kind of related to the quantum information.
Well, I think the important thing, there are kind of many ideas about how possibly quantum space-time should look. It's extremely difficult to take these ideas and make them consistent with the things that we already know about space-time. So we know the symmetries of space-time, they are verified with great precision. So whatever idea you have, it should mesh with the well-established theoretical ideas we already have found through many, many experiments. And so the remarkable thing about string theory is that actually it's able to make this connection. So it preserves all the symmetries that we know that are there in nature. It gives general relativity as it be verified with great precision. And the remarkable thing is that we are learning now that there might be very different ideas about how space-time would look like at the very smallest distance scales. And I think the most convincing argument is it will not be anything related to space and time. It's something that is very, very, very different. And basically it's something very comparable to the way the thermodynamical laws emerge out of the interactions of atoms and molecules. This is like trying to understand space-time in terms of kind of atoms and molecules of space-time that together build up space-time. And I think that's what we have seen in many examples. Of course, these are only examples. We don't have a description that would do this in great generality. But I think it gives us confidence that we have to be very radical about thinking about the fundamental degrees of freedom of string theory.
Okay. Very good questions. Fantastic talk. Let's thank Robbert again.